identifies various motifs, structural and chemical motifs within the material. So this could be just one individual atoms, which are called one body motifs, or these could be two body motifs, this G2 here, or three body motifs. So two body motifs captured information about interatomic distances. Three body motifs capture information about angles between bonds. One could, in principle, have four body motifs, which would capture information about dihedral angles between planes of atoms, etc. And finally, and after you have identified these motifs, constructed them, and there are specific functions that represent these motifs. G1 is just the atomic number, G2 is inverse of the distance between two atoms, G3 is the angle or cosine of the angle rather. Once you have identified these motifs and calculated these quantities, what is done is sort of to spread them using some kernel, and the most widely used one is the Gaussian kernel. So after constructing a G1 or G2, you construct these functions D's, D1 or D2 by creating these Gaussians with some appropriate widths, sigma 1 and sigma 2. What are these widths? There are no recipes. One has to find out from experience. So we will construct these and see how these can be set when we work hands-on. So after you have, so these are now functions of x, and depending on what quantity you are sort of spreading out, you fix the range of your x. Of course, when you are working with G3, cos of some angle, so this can only go from -1 to +1, so you already know what the range of that x would be. And then you have constructed these quantities for various elements, various pairs of elements, various triplets of elements, and so on. After that, you add them up all. So you have the one body MBTRs, the two body MBTRs, and the three body MBTRs, and so on. And how do you fix these weights? So these weights WIs are determine how these D's are to be combined linearly. The most reasonable way to do that is to fix them in such a way that distant atoms contribute less. So when, for example, you are working with two atoms that are close by, they should contribute more. When they are far apart, they should contribute less, and so on. So you choose weights which die out exponentially with distance, pairwise distances. And then you construct, and I showed you how these can be rationalized. These are MBTRs for k equal to 1, so that is one body, two body, and three body MBTRs for a water molecule. Fine. So that was the last sort of what we called global features that we discussed. The next two features that we will discuss are local features. So what do we mean by local features? Local features take into account or capture information about structure or atomic structure around some central atom. The first one, at least, captures atomic environment about some central atom. So first, let us try to understand from a science perspective why such local features could be important. All right. Yeah. All right. So this is an example that those of you who are from chemistry background would obviously know, and those of you who have read enough about magnetism in crystalline solids would also have encountered it. often what you, so what I'm showing here is you can consider it to be a transition metal complex. So you have a transition metal at the center, and then you have some other atoms surrounding it in some particular symmetric fashion. When you consider any atom, in particular a transition metal atom, just an isolated atom, it has 5d orbitals, right? You know that. And energies of these 5d orbitals are identical. So that is here. They are all here. Same energy, at least in hydrogenic atoms. What do you mean by hydrogenic atoms? We are ignoring any interactions between the electrons. So when we ignore electron-electron interactions and there are nothing else around it, an isolated atom has all the d orbitals to be degenerate. But then in a complex, and the same situation arises in many solids, oxides, for example, chalcogenides, for example. These anions, this could be oxygens, this could be chalcogen atoms surrounding the central transition metal atom. So these are negatively charged, and the transition metal is the cation in this case. Now, depending on the symmetry or how these anions are arranged around the transition metal atom, the degeneracy of the d orbitals are lifted. And what is shown on the left panel of this figure is that this is an octahedron of the anions around the cation. And in this particular arrangement, degeneracy of the 5d orbitals are lifted in this particular fashion. dxy, dxz, dyz orbitals have lower energy, and dx square minus y square and dz square have higher energy. How these degeneracies are lifted can, of course, be understood or read out from the point group symmetry of the structure around the transition metal atom. So the octahedron has OH point group symmetry. This structure on the right is a tetrahedron, and in this tetrahedral symmetry, you have the similar splitting. These three d orbitals are degenerate: dxy, dxz, dyz. Dx square minus y square and dz square has different energy, but the ordering of the energies flipped as compared to the octahedral point group. Now, group theory, of course, I'm not going to get into group theory here, but what I'm just trying to tell you is that just by looking at the group tables, you can figure out how the degeneracy will be lifted. But what the group tables, character tables will not tell you is that which one would be higher and which one would be lower. That basically depends on charge distribution. And you can easily argue that if you have this metal atom as cation with anions around it, then these would be the order of splittings in the two cases. But that's a matter of detail. But now what? So you have the degeneracy of the d orbitals lifted. That's the important point here. Why is that consequential? What does that lead to? So what that leads to is the following. So here is a particular complex. But the details are not important. What I'm trying to highlight here is that suppose you have two situations. In one situation, in both cases, you have octahedral symmetry. So this is the splitting you have, 3 here, 2 here. These are called T2G levels. These are called EG levels. These terminologies come from group theory. These are exactly these orbitals that I showed you, dx square minus y square and dz square at higher energy, and these other three at lower energy. So these are the T2G orbitals, these are the EG orbitals. Now consider two situations. In one case, this splitting is small, relatively small. Of course, you have to specify relative to what, we'll come to that. In another case, this splitting is very large. And with respect to what? With respect to what is called exchange splitting. Now that requires some explanation, so I will not get into that. So I'll give you a simple sort of intuitive picture of it, which is that suppose you have 6 electrons in both cases, but in one case the splitting is small, in another case the splitting is large. So in this case, first you put 3 up electrons here, and then the next ones, because the splitting is not very large, you can still put those here and the sixth one here. So this will be the spin configuration when the crystal field splitting. So this splitting is called the crystal field splitting is small. When this crystal field splitting is very large, what happens is that so you would rather put all 6 electrons in these T2G states rather than occupying these higher energy EG states. And the result is that in this case, on the left, the net spin on these complex would be 4 unpaired electrons. So that would be spin 2, whereas on the right hand side, spins are completely paired up. So spin 0. So that is the difference. So whether you have net spins, whether you have magnetic moment in a system or not, depends on the extent of this crystal field splitting of the of the d orbitals on a transition metal, as compared to exchange splitting. What is exchange splitting? Very quickly, very briefly, when you have electrons in the same spin state, the system gains some energy as opposed to when they are in opposite spin state. So here there is some energy gain because you have 4 electrons in the same spin state. But then if this energy gain is large compared to this splitting, then it makes sense for the system to be in this state. But if this energy gain is little compared to this, large splitting, then it makes sense for them to be paired up rather. So small crystal field splitting versus large crystal field splitting, large spin state versus small spin state. So magnetization, magnetic moment on a transition metal crucially depends on the crystal field around it. And crystal field is a local effect. It doesn't matter what is happening at other places in the crystal. It depends on what is the environment of this atom just around it. So that is one example. One can give other examples as well, but let us stick to this. So this is one example where the local environment is important. And if you are, for example, interested in capturing, predicting magnetic properties of materials, you would like to capture this information in your features. So that is the motivation for having local features. Now, we will discuss 2 different kinds of local features. The first one is called atom-centered symmetry functions. Now, obviously, the name already tells you that some atom is at the center. So you put one atom at the center, like our transition metal, and then you look around for symmetry or construct functions that depend on the symmetry of other atoms surrounding this central atom. So here are the steps. You identify a central atom, and then after that, you construct various 2-body and 3-body functions centered around it, including atoms up to some cutoff distance. Of course, you don't want to go very far, it hardly makes sense. That should be obvious from the discussion we had. So you want to set a cutoff, and within that cutoff distance, you want to construct various 2-body and 3-body functions around your central atom. And your central atom could be your transition metal cation, for example. So what do these functions do? They capture information about pair distances, angles in the locality of the central atom. How exactly? We will see. So what you do is you don't, or the way it has been defined in the literature is that you don't put a strict cutoff function. It's not a step function that I consider everything to be, with the same weight within this cutoff distance and anything outside is left out. No, the cutoff function that is used is this one. How does it look? I have a plot for it, so I'll just show you. So focus on the left top figure. This is the form of the cutoff function as a function of R over RC, its argument. So you have to firstly set some RC, which you can set from your chemical intuition. So once you have set RC, this function goes to 0. Actually, it's a cost function, so it has many zeros, but the first time it goes to 0 is when R is equal to RC. So up to a distance RC, atoms will have some contribution. Beyond RC, they don't have contributions. And contributions are not weighted equally. Weights of contributions of atoms fall off as the distance increases. So that is what this cutoff function means. Fine. So that is our cutoff function. Then what do we construct? We construct two-body functions. Okay, so these are some of the two-body functions that are defined. So there are three different kinds of two-body functions. It's not like one two-body function. No, there are three different kinds of two-body functions that have been defined and used in the literature. The first one is called G1. Although it's called G1, it's not a one-body function. It's a two-body function, mind you. It is just a sum over these cutoff functions, and it has a tag Z1. So which means that you have a different two-body function. So central atom is chosen. That is what it is. After that, there is one G1 for each type of chemical element that you have in the system. Okay? And the sum goes over for Z's of a particular value. So Z equal to 1 would give you a sum over all the hydrogen atoms in the system. Z equal to 2 would give you sum over all the helium atoms. If you have helium atoms, you typically don't, but it doesn't matter. You could have one sum over all the oxygens, you could have one sum over all the nitrogens, if you have oxynitrides, etc. So you get the point. Then G2 is the second two-body function, again labeled by different Z's. So you have one G2 function for each Z1. And here, what is summed over is slightly different. Here, what you are summing over for G1 is just the cutoff function. Here, along with the cutoff function, you have this this Gaussian factor with Rij minus Rs squared. Now, what does that do? If you can choose Rs appropriately, you can capture information about atoms at a particular distance from your central atom. So let us see how this function looks like, this part. Not summed over various atoms, but one of these. So this will give you a physical intuition as to what this function is capturing. So I'm talking of the top right panel of this figure. So what I have plotted is the G2 function, say for some particular Z, doesn't matter. And different lines with different colors represent these plots for different values of eta and Rs. Again, I'm going back and showing you what eta and Rs are. So eta is this factor here in the Gaussian. So inverse of square root of eta is some length scale which determines how fast it falls off. And Rs is some particular distance. So if Rs happens to be equal to Rij, it has the maximum. So it would have a peak if Rs is equal to Rij. So Rs is something you choose, and Rijs are the interatomic distances you have in your structure. So, sort of clever thing to do is to plot these functions for different values of Rs for some reasonable values of Rs. Okay, so if you have worked with materials, if you have worked with chemical, you know, chemical systems, molecules, you have some sense of what these Rs are. Say 2 angstrom, 3 angstrom, whatever. 6 is too much, but I put 6 anyway. So you see, I have plotted 6 curves here. 2 different values of eta and 3 different values of Ra. So you have total of 6 combinations. And in every case, so let us look at Rs equal to 2 curves. For eta equal to 1 and eta equal to 2, Rs equal to 2. So these are these 2 curves here. Okay, if you can see my pointer, these 2 curves. And their widths are different because eta are different. When eta is 1, the width is more, the bluish curve, and the reddish curve has a lower width because eta is larger, but they both peak roughly around 2, not exactly because there's this cutoff function that multiplies it, but roughly around 2. These are the curves for Rs equal to 3. So they peak around Rs equal to 3 and so on. So if you can choose Rs to be equal to or roughly equal to the nearest, where am I going? To the nearest neighbor distance here, then you pick up contributions from these atoms. Okay, that is the idea. And so what you do is, since you do not exactly know what the values of these nearest neighbor distances are from this cation to the anion, you can construct these functions for few different combinations of etas and Rs, as I have shown. And when Rs is equal to 6, because I used a cutoff Rc equal to 6 here, these make very little contribution because the cutoff function has already fallen off close to 6. So you pick up, so the point is you pick up contributions from pairs of atoms. Similarly, here is G3, another two-body function. Note, although I have a cos function here, it is not an angle between bonds. It is just a way of, it's a cosine of the interatomic distance Rij with some factor kappa. Again, you can plot various plots for different values of kappa once you have fixed your cutoff distance Rc. And if you have large kappa, that gives you a larger, for larger kappa, the argument of the cos function is large, so you have more fluctuations, more zeros by the time you reach your cutoff Rc. So all three of these functions, what they are doing is they are capturing pairwise information, pairwise distance information about the central atom. And you construct one such function for each chemical element Z, indicated by Z1 here. All right. So this is about two-body functions. Now, three-body functions. Looks a bit complicated. You will find the expression. I'll share these slides as before, and you can find details of this in this paper. But let me just state what this is. So this basically, this theta is the angle between two bonds, just as in MBTR. So Rij is one bond, and Rij and Rjk. These are the two bonds, and then theta is the angle between them. And then you construct such functions which depends on both the interatomic distances through this Gaussian factor and also these cutoff functions, but also this angle between the two bonds. And you construct one G4 function for each pair of Z1, Z2. Okay, so Z1, Z2 is a particular pair of chemical elements. A similar looking, somewhat different. So one of the cutoff functions is missing. One of these, in the exponent, one of the r squared functions is missing. Otherwise, the angular part is the same in G4 and G5. So the essential idea here is to capture information about angular environment, about your central atom. So this is how the G4 function would look like for different values of zeta. If zeta is large, it falls off faster. But in any case, by the time theta is pi, you have 0. The function goes to 0. So theta would pi would mean a 180-degree angle. So this is if you have two atoms, which is an ideal case. So here is the central atom. Here are the two atoms. If they are overlapping, which never happens in chemistry, so your angle is 0 as this bond deviates. This angle increases, and when it is 180-degree, it's on the other side. So then also that function goes to 0. So this is how you capture information about bond angles around the central atom. So these are the 5 functions that have been defined, which together constitute atom-centered symmetry functions. Now, what I said is that there are, first of all, 3 different two-body functions. There are 2 different three-body functions. So how do you organize them? The way you organize them, or the way they have been organized in the particular library that we will use later on to create these features, is the following. First, all the G1s are calculated, or rather I would say you calculate all the G1s, you calculate all the G2s, all the G3s, G4s and G5s, and the question is, how do you concatenate them? How do you attach one after the other, in what precise sequence? So that is something I'm trying to explain now. All right. So that is what I'm trying to explain now. So first of all, G1. So you have one G1 for each chemical element. So you can arrange them in increasing order of Z. Or yeah. So what they are doing is, let me explain it again. First, you look at Z1. So it is better explained in terms of an example. So let me go to this example. Doesn't matter what this system is. It's an example. You probably will not have a real chemical system with these species, but the species present in your system are 1, 2, 3, and 5. These are the Z values. So 1 is hydrogen, 2 is helium, 3 is lithium, and 25 is manganese. So this is your system. Then, sorry, yeah. Now I have it. So then what I'm trying to do is I'm trying to calculate ACSF around the metal atom, the transition metal atom, which is the manganese, that is Z equal to 25. So leaving out Z equal to 25, I have 3 different other elements with Z equal to 1, 2, and 3. So this is how then the two-body quantities are organized. So this part is for Z equal to 1. First you write G1, then you write G2, but then you can have different G2s for different combinations of eta and Rs that we just discussed. So you write all the G2s for different combinations of etas and Rs. Then you have G3, and the only parameter that varies in G3 is kappa. So you concatenate all the G3s for different values of kappa that you have. So you complete this for Z equal to 1. Then you go to this block which is for z equal to 2 and you follow the same procedure. First G1, then all the G2s, then all the G3s, then for z equal to 3 and so on if you have more. So these are the top row is this contains the two body functions. Now the three body functions. So you have Z1, Z2 pairs. So you have a 1, 1 pair, you have a 1, 2 pair, you have a 1, 3 pair, you have a 2, 3 pair. For the 1, 1 pair, so when both neighbors are hydrogen, you have G4 functions, you have G5 functions. And you can calculate G4 functions for different combinations of eta, zeta, and lambda. So you write them one after the other. Similarly, for G5, different combinations of eta, zeta, and lambda, and you concatenate them. Then comes the 1, 2 block, then comes the 1, 3 block, and so on. So the example that I showed you, species 1, 2, 3, 25, ACSF constructed only around the manganese atom with Z equal to 25. So the one body terms, you would have three different G1s, you would have 6 different G2s, because, okay, so let me show you that example once more. G2 parameters eta and Rs. I have chosen one zeta, 1 eta, 1 Rs. Eta equal to 1, Rs equal to 2. Then the G3 parameters are defined. Here G3 parameters is kappa. So I've chosen two values of kappa, 1 and 2. G4 parameters, eta, zeta, and lambda, all are set as 1 here. Similarly for G5, 1, 1, and 1 for eta, zeta, and lambda. Now, so note that I have 1 eta, 1 Rs for G2, two values of kappa, and one set of eta, zeta, lambda for both G4 and G5. So when I have that, I have 3 G1s because I have 3 different chemical species as neighbors, 6 different G2s because I have 2 values of kappa and 3 different chemical neighbors, 3 G4s because 3 different neighbors, and so on. So this should be actually G3. What I meant here is G3. I'm talking of two body functions. That was a typo. Yeah. Because I have only one combination of the parameters. Two body terms, 3 different G4 and 3 different G5, because given Z values of 1, 2, and 3, you can form 3 different combinations. So that is how you construct the ACSF. What is the library to use, how it is calculated, that is a matter of technical details that we will get to after we finish these discussions. So this is ACSF, which captures information about chemical environment, about a central atom, and quite often, I mean, it would either, one example I already showed you when you were interested in magnetic properties, magnetization on a transition metal atom in some complex, in some environment surrounded by anions, for example, or this could be useful when you maybe calculate absorption energy of some atom on some surface or something, where the local chemical environment is more important than what is happening globally at distant places in the material. Okay, so that is ACSF. The next local feature that we will discuss is called smooth overlap of atomic orbitals. Now this is a bit involved, and I will go slowly. Maybe I will not be able to finish it completely today. So we'll take it up, this thing and something else next time. Okay, the idea of smooth overlap of atomic orbitals is completely different from ACSA. The very first thing you do is you construct what is called atomic density field. So what is a field? It's something that is a function of r. Given a coordinate, it has a value. And in this case, it's a density, so it's a scalar. So it's a scalar field. And you can construct such a field for each chemical uh, element that you have in your material. And here is the general formula for doing this. So you pick up contribution when R is equal to some Ri, and then you multiply that with some weight. And of course, your Zi, the element at Ri, has a specific atomic number Z. So you construct a different atomic density field for each type of chemical element denoted by the atomic number Z. Now you can choose weights, these W's, in various ways. You can choose all of them to be ones, and in that case there isn't much of a R dependence in this. But what is meaningful is to construct Gaussian smeared atomic density field. What does that mean? That as you move away from the location of the atom, its contribution to the field decreases, and it decreases as a Gaussian function. I probably missed some factors, and let me just check it. Give me a minute. Yeah, so I missed square here. Yeah, so it's a Gaussian function. I had missed this square here, r minus ri squared. So as you move away from ri, contribution of that atom to the field goes down. So this is called Gaussian smeared atomic density field. Now, if I'm interested in a particular point in my material, now in this case, it doesn't have to be a particular atom. No atom necessarily has to sit at that point of interest. It could be any R. Okay, so I just look at that rho Z of R. So uh, I go to a point R, and then I expand this function, this density function, around my point of interest in terms of some basis function. So rho of R is some function of vector R, so which has the radial part R and theta and phi, the angular parts. And if I assume that this function can be expressed as products of some radial part and some angular part, then I can expand it in terms of my basis functions. Now here is that expansion. So this is something you must be familiar with. It's a very general statement that rho of z is a linear combination of products of radial functions and angular functions. And as long as the angular part is square integrable, a good basis function, a natural set of basis functions to expand the radial part are the YLMs. Let me be consistent with my notation. Yeah. All right. So spherical harmonics, YLMs, are the natural basis functions to expand the angular part of the function. And this, in this expression, G and L are the radial basis functions, and C and Lm are the coefficients used in the linear expansion. So that is it. So rho of R for a particular Z is being expanded in terms of radial and angular basis functions. If and only if the YLMs are orthonormal. Okay, so you must have, those of you coming from physics and chemistry background, have done your quantum mechanics or some mathematics. You would obviously know that YLMs are orthonormal functions. YLMs defined in this particular way are orthonormal functions. And only if G's are orthonormal, then and assumed to be real functions, then the CLNLMs can be written like this. So I have not used the Z index here. You just assume that there is a Z index hanging on C and rho. And this is a volume integral. So once we know, so why are we after C? If we know C's, then we can construct rotationally invariant features which represent local information about the point of interest. That's our target. But we can do this, we can calculate C's in this fashion only if G's are orthonormal. Now, are G's orthonormal? What are the G's that are used generally? In principle, you could use any G, but the problem is that what is convenient in analytics is not necessarily the most convenient thing in numerics. So if you use some general polynomial, that may not be the best thing to do when you do it numerically. Numerically, Gaussians are a very convenient functions to use when you have to do integrals. So in this library describe, which we will get familiar with, and in fact this is the library we will use to construct all the features, or except all the other features that we are discussing. Okay, so this is a library in which all of these things have been coded in. So what you have to learn is how to use this to construct this feature for a material you have. And so, the immediate question that we are discussing is, what are the radial basis functions G's that we are that are normally used, that have been sort of encoded in this library describe? The first one is spherical primitive Gaussian orbitals. Okay, that's the first type of basis function, radial basis function they have used, which is this. So betas are some coefficients. So G is not a single function of R. G is constructed as a linear combination of some 5 NLs. Okay. So what kind of functions are phi's? Phi's are Gaussian functions with this factor R to the L. So that is what is called, these are called spherical primitive Gaussians. So G and L's are constructed as combinations of spherical Gaussian functions. And alpha n's are the decay parameters. And these are already sort of hard-coded in describe. They are chosen in such a way, or it is chosen in such a way that the function phi decays to r to 10 to the minus 3 at some cutoff radius r cut, and probably one can play with r cut, or it is already sort of hard-coded that I have to check. But if you choose some R cut, remember this is a different R cut. We had a different R cut for ACSF. This is a different feature we are talking about. So whatever R cut you set, alpha n is chosen in such a way that phi n's decay to 10 to the minus 3 at that R cut value. And these phi's are not, and the g's constructed from these phi's are automatically not orthonormal, but they can be made orthonormal through a procedure called Loudon orthonormalization. So basically, you have to choose your betas carefully, and the betas are just, if you choose your betas to be scalar products of phi's, then you can show that these are orthonormal. So I leave that for you to figure out. And in particular, the dscribe library has coded up to L equal to 9. So you can choose how many L's to use. So when I go back to this, you are doing a sum over n's, and given a value of n, L goes from goes from 1 to some L max, and then m, of course, in YLMs will go from minus L to plus L. That, of course, is fixed by the spherical harmonics. So then they have coded up to L equal to 9. All right. The second type of basis function, radial basis functions they have used is this one. Polynomial functions, which is simple polynomials, r minus r cut to the power whatever, and this whatever is cubic or higher. N is a positive number. N is 1, 2, 3, etc. So you can use cubic or higher polynomials. There is no L's involved in this case in the G's. Again, alpha n's are used the same way, and again these are not obviously orthonormal, but you can make them orthonormal by choosing your betas appropriately. So, and in this case, they say they have coded up to L max equal to 20. So this is L max. I'm sorry, we have still not got to ACSF, but essentially, let me see if we can. Yeah, want to discuss some more detail, perhaps. Yeah, little bit of more mathematical details I want to give you, but this will take some time, so I don't want to start those today. So for today, you just carry this much, that as far as this smooth overlap of atomic orbitals or SOAP local features we are considering. Step 1 is to construct the atomic density for each Z, then expand rho Z in terms of radial and angular basis functions. And what we claimed is that if the radial basis functions are orthonormal, then the C's can be expressed in this way, but generally G's are not orthonormal, because for numerical convenience, the basis functions that are chosen are either spherical primitive Gaussian or some simple polynomial forms, which are not orthonormal. So, but they can be made orthonormal if betas, these coefficients, are chosen as depending on this. So maybe this. I will get back to this point in the next lecture. How to make this orthonormal, or how this makes it orthonormal. And so the same thing for the polynomial thing. So how do these functions look like? So these are some plots of the radial functions. This A panel is for the spherical primitive Gaussians. I don't think the visuals would give you a lot of information, but you can at least make some guess that when n equal to the one function has p close to 0, and for I think they meant a equal to 1, 2, 3, and 4. And then this is how this would look. This figure is taken from the paper, but I suspect that what they write as n equal to 1, 2, 3, 4 are actually L values. And this is the polynomial function, or these are the polynomial functions for different values of n. No, actually this is right. So this is n. So n varies from 1 to 4. And the top panel is for L equal to 0. The middle panel is for L equal to 1. And this panel is for L equal to 2. So the point is that different functions has peaks at different distances from the origin. So therefore, if you have a combination of these, then they capture information about the neighborhood of your point of interest up to some distance, because these functions fall off rapidly. And the YLM functions would take care of the angular distribution. So together, they capture information about the local environment around the point of interest. So, yeah. So maybe I should stop here. Two features we discussed today. One is ACSF, atom-centered symmetry function, and the second one is smooth overlap of atomic orbitals. So in the next lecture, I will complete this discussion of SOAP, how finally we construct rotationally invariant set of features. And then the last feature that we'll talk about is also a global feature, but it is very, very different in spirit compared to anything that we have discussed so far. It's a very simple, intuitively clear, sort of pictorial, if you like, representation of the crystalline structure of the material. So with that, our discussions on features will finish. And when I start next lecture, we will see how to access materials data and how to work with them to construct these features. So some questions I see: what combination of eta, kappa, lambda, RC values should we choose while performing ACSA featureization on the data's chemically different molecules? These are not hyperparameters. These are parameters that are set while constructing your features. Hyperparameters are about some aspects of the model. These are not part of the model. These are part of the features. So you have to fix them when you fix the features. So the suggestion is that you don't use just one set of eta, kappa, or lambda. Lambda is usually +1 or -1. You don't play with lambda. RC also, depending on the system, you can set a fixed value. It comes from your chemical intuition. It's very unlikely that anything beyond, say, 5, 6 angstroms would play a role in the local chemistry. Whereas eta, kappa, RS values can be played with, and that is why I showed you that figure. This is better. So you can construct G2 for different sets of eta and RS. Similarly, G3 for different kappa different kappa. G4 for different sets of eta, zeta, and lambda. But as I said, lambda is usually taken as +1. So once you have these quantities calculated for different sets of your parameters, you are capturing a whole lot of useful information. I hope that answers your question. Okay, so that's all for today, unless you have other questions, and we'll meet on Wednesday.